Welcome back to the next video, everybody. Today, we're finally going to conclude the proof of Theorem 9, hence of Langlands-Tunnell. We're going to do that by looking at the last remaining case, which is the octahedral case, and I really like this proof as well. So recall, what are we trying to prove? Theorem 9, let F be a number field, and suppose rho from the Vega group of F to GL2 of C is a solvable irreducible rep. Then there's a unique irreducible automorphic cuspidal rep, pi of rho, with local components pi sub v of GL2 of the Adels of F, such that trace of rho of Frobenius at V is trace of the local Langlands class T sub pi sub V for almost all places V of F. We've already proven the theorem in the case the image of rho in PGL2 of C is A4. That was the tetrahedral case. We spent 2 videos on that. By proposition 3 several videos ago, the only other possibility, given that rho is solvable irreducible, which it is that the image rho of W sub F in PGL2 of C is actually S4. And this is the so-called octahedral case. Okay, so how do things change this time? Well, this time the pullback of the normal subgroup A4 and S4 is the Vega group, let's call it W sub E, of a quadratic extension, E over F. So it's not a cubic extension this time. Here's how the diagram of groups and Vega groups and image groups changes. So we have an exact sequence on top, 1 to WE to WF to the Galois group of E over F to 1 as usual. But this time the Galois group of E over F is isomorphic to Z2, not Z3. Okay, and the image of W sub F is S4 by assumption. And then by what we just said, this guy here should be A4. Okay, so I see that rho sub E, which is the restriction of rho to the Vega group W sub E, falls under the tetrahedral case. And so pi of rho sub E already exists and is irreducible cuspidal as a representation of GL2 of the Adels of E by the previous case, by the tetrahedral case. So that's good. So I also know that pi of rho sub E is Galois group of E over F invariant, okay, essentially by construction. So by theorem 10, pi of rho sub E should just equal the base change from F to E of pi sub I for now 2 different irreducible cuspidal representation, I guess, classes pi sub I of GL2 of A sub F. And that's because now E over F is quadratic. We had 3 classes before, now we have 2. Okay. Unfortunately, this time we cannot distinguish the pi sub I by their central characters because we have pi sub 1 is pi sub 2 tensor omega for some quadratic character omega on this orbit space here. And so we still have the relationship omega pi sub 1 is omega pi sub 2 times omega squared. But the thing is, what happened? But the thing is, omega squared is 1, right? So before we had this relationship, but omega was a cubic character. So omega squared wasn't 1. And so we could distinguish the representations by their central characters, but now we can't. Now omega, the central characters of pi 1 and pi 2 are the same. So what do we do? So most of the work, just so you know, done up until this point was done by Langlands and others. But if we're splitting up the work between Langlands and Tunnell, and we're only attributing the work to one of those 2 people, most of the work done so far has been by Langlands. So Tunnell's contribution is in this octahedral case. He gets around this issue by appealing to a different kind of base change. So theorem 11, maybe octahedral base change. If L over F is cubic and not even necessarily Galois, then each automorphic cuspidal representation pi of GL2 of the Adels of F does have a base change lift big pi to GL2 of A sub L. That is, big pi, which is the base change lift from F to L of little pi, is automorphic. And for almost every place V of F and every place W of L lying over V, pi sub V, the local component of pi at V, which, you know, we can think of as pi sub V of sigma sub V, although I probably should have called this rho sub V, but that's okay, implies big pi sub W is little pi of the restriction from L sub W down to F sub V of sigma sub V, or rho sub V, if you like, whatever. Okay. And just to recall, what are these sigma V's or rho sub V's? They're the Langlands parameters of pi sub V's. They're the restrictions down to the local Vega groups W sub F sub V. Okay, so you can do base change lifts with kind of arbitrary cubic extensions, essentially. All right, so for a proof, you can see Jacquet, Piatetsky, Shapiro, Shalika. But the proof is really analogous to Jacquet's proof of base change over GL2 of kind of arbitrary quadratic extensions. So you can see Jacquet automorphic forms on GL2 part 2 for that. Okay, how about the trace formula? Does that have any part to play here? Well, the trace formula methodology fails here, because L over F, as I said above, might not be Galois. And so there won't be a way to define the twisted trace from the trace formula video. So Tunnell just gets around this. He says, all right, I'm just going to introduce a new field extension, L over F. It's going to be the cubic non-normal subextension of K over F fixed by a CeLO2 subgroup of order 8 of S4. What is this K here? K is the extension of F corresponding to the Galois group S4 in this diagram of exact sequences up here. So we're just using Galois theory. Okay. By the way, how do I know there is an extension? Well, that's by the solvable case of the inverse Galois problem. If you want to read about this, you can read Shafarevich, the embedding problem for splitting extensions. Okay, so this L actually exists. Perfect. All right, so now we have this diagram, and I'll let you work out the details, but it all follows from what I've said so far in the diagram of exact sequences above. Set M to be the compositum of in K of L and E, so the smallest field containing L and E in K. And you get the following diagram. You have F in E and M in K. You have M is the compositum of these guys. This Galois group is Z2. This Galois group is Z3. This Galois group is A4. This Galois group is S4. And then you'll have to work this part out, but this Galois group here is just D4, and this Galois group here is just S3. Okay, that's just a bunch of group theory and Galois theory. Okay, perfect. Here's the crucial result that we need. In fact, this is all we really need to prove, right? There's a unique I that's either 1 or 2, such that the base change lift from F to L of pi sub I is the pi of rho sub L that we're after. And this is the correct choice for pi sub pseudo of rho. In other words, we're done. In other words, if we can prove this, the octahedral case is done. We found out there's a suitable pi sub pseudo of rho, and it equals the pi of rho sub L that we need to finish the proof of theorem 9 in this case. Okay, how do you prove this? First of all, pi of rho sub L does exist because our CeLO2 subgroup defining L is just D4. So rho sub L is monomial by proposition 3 in theorem 6. Okay. So similarly, the base change from F to L of pi sub I also exists for both I's, and that's just by theorem 11. That's by this octahedral base change up here, right? Okay, perfect. To prove the lemma, the first thing you do is you check essentially pretty easily and by definition of base change that there is a transitivity of base change in the following sense. If I take the base change from L to M of the base change from F to L of pi sub I, that is just pi of rho sub M, as you might expect for both I's. Okay. Now, the base change from F to L of pi 1 and the base change of F to L of pi 2 have the same quadratic base change to M. We talked about that above, right? And so we find by the discussion under the diagram of exact sequence in the tetrahedral case that the base change from F to L of pi 2 is isomorphic to the base change of F to L of pi 1 tensor some twist omega of M over L. I claim then that it must be true that these base changes are distinct. Why is that? If they're not, then this reads the base change from F to L of pi 1 is isomorphic to itself tensor this twist here. But then there's a lemma in Langlands base change, lemma 11.7, that says pi sub 1 must be monomial if this happens. Okay, why is that a contradiction? By parts 1 and 2 of theorem 10, if this is the case, then pi of rho sub M, being this kind of double base change here, this transitive base change, is not cuspidal. Okay, well, here's the thing. The image of rho sub M, the restriction of rho to the Bay group W sub M, in PGL2 of C is just S3 by the above diagram that I drew up here, right? Okay, so it's S3. So the image of rho sub M in PGL2 is S3, which is just D3. Well, that means by definition, that implies, because the image is dihedral, that rho sub M is monomial, and it's irreducible by proposition 3. Okay, well, that means pi of rho sub M then, the pi associated to rho sub M is cuspidal by theorem 6. So I'm citing endless theorems here. This is the contradiction, okay, because it wasn't cuspidal. So it is true that the base changes from F to L of the pi sub I are distinct for I equals 1 and 2. And in fact, that they're each cuspidal by theorem 10 as representations of GL2 of the Adels of L. And we know both of them yield pi of rho sub M after base changing to M. I talked about that above on the previous slide. Okay, now it's also true that the base change from L to M of rho sub L is pi of rho sub M. Okay, and so by uniqueness of base change, pi of rho sub L must be the base change from F to L of pi sub I for exactly one I. It's for one I and then exactly one I by uniqueness, because these guys are distinct. That's crucial. It's crucial that these guys be distinct. Okay, here's the epic conclusion. What do you have to check now? all you have to check now is that pi of rho sub L is the correct choice for pi sub pseudo of rho. That is, you have to check that pi of rho is pi sub pseudo of rho. And I kind of just claim I don't have to do this at all, because the proof is almost identical to the tetrahedral case, which we went through. In fact, I'll even tell you it's easier, because you don't have to use symmetric square lifting. You don't have to lift to GL3 of C at all in the proof. That said, if you still want to see the details, check Tunnell, Artin's conjecture for representations of octahedral type for the details. This finishes the proof of the lemma, hence the proof of the octahedral case, hence the proof of Theorem 9, hence the proof of Langlands-Tunnell. So we are done with this chapter. Langlands-Tunnell is proven if you believe incredibly deep results like a bunch of these Langlands specific cases and instances of Langlands functoriality, and in particular, also if you believe the trace formula. I mean, these are very deep results we took for granted, but we don't want to get too far afield here. So next week, I will go on to the next chapter in my notes, chapter 7, which will be based off of CSS, Cornell, Silverman, Stevens, chapter 7. And that chapter will be on Sayre's conjectures. So I'll see you next week, and thanks for watching.